Hi. Maybe you unmute. We are not hearing.
We're going to start by reminding ourselves that total energy plus total energy. And we usually write that as total energy is half mv squared plus u, where u is the potential energy depending on where we happen to be, whether it's a gravitational field, an electric field, or whatever. We can also write half mv squared as p squared, 2n plus u, because you may recall that p is mv. Therefore, p squared is m squared v squared. Write that by 2n, you get half mv squared. Okay, we're also going to be summary is e to the power k6 minus t. And you'll need to see another one like it to establish why we use that particular form of rate. Now, let us differentiate that way with respect to x, holding time constant. If we do that, differentiating an exponential function is very simple. You take the two terms, the I and the k, which are in front of the x, and you bring it down in front of the exponential term. It simply becomes ik times e to the ikx minus t, which of course is one and the same thing as saying ik times the original value of psi. Okay, we'll keep that. Now we're going to differentiate again. So we're going to take the two sides with respect to the x squared. That means you bring down ik again. Squared. Now let's just remember that is equal to because I'm defining k as lambda. And if we work it through, we know from the formula that p equals h1, so p equals h over lambda. Therefore, p equals h over lambda is 2 pi over k. Pi is just another version of this constant. Now we've got p equals h bar k, so k is p over h bar. So now we can say that d2 psi by dx squared is ik squared, of course, minus k squared, minus k squared, minus p squared, plus psi. Multiplying through by minus, we get minus h bar squared into psi by dx squared equals b squared psi. But you will recall that e equals b squared over 2n plus u. So, if we have that the formula, then we can say psi. We can say that e psi is b squared psi plus u psi multiplied by psi. two sides like this plus you size. Is the time independent shredding and and we can get further, we can do time independent shredding and regression by finding ourselves at G equals 7.
So guys, just to welcome you one more time. Sorry about that. Yeah, so we have gone through that first bit of the derivation. So we'll explain what a few of the things mean in that derivation. So you've heard of, you may not have heard of, you have heard of Euler's identity. So you can express an exponential function by a cosine and then what? A sine. Eh? So those are Euler's identities. Now, using the Euler identities, we can be able to have the waves which we had in terms of sine and cosine, the wave function as a function of what? As a function of the exponential function. So that was what is being used there. So let's see. So the Euler formula is so in the meantime, we welcome the people officially. Dodwa Faruku, Jones Davy. Is it Davy Jones? There's some kind of movie it's called Davy Jones. I think it's either most of those pirates movies. Kwezi B, Julius Sechewa, and Ndugwa. Okay. It would be hard to guess. Odapa Ambrose, Mwanja Charles, Sempija John, Were Henry. Yes. So in English, it sounds like we are. So, Millicent Inebe, Kashaba Godwin, Prince Wakinovich. Who else do we have here? Maweje David. Then you have Mr. Daniel Sansa making his debut. Those who know football about debuts. You have Keith Membe. Keith, you're welcome. You have Mugisha Timothy, like one of the aspirants. Joan Nabukenya. Ayebara. Is that Ayebara or Ayebare? I don't know what Ayebara means by that. Ayebara Aaron, Akwede Stella, Catherine Namboga, Popular Tech. Last time he typed his name in the chat. Then we have Kalemba Yan Kennedy, Daniel Sansa Chebambe, Tumaise Chris, Nambi, Swabra, Esther, Patricia Nyambel is also here. And then have we welcomed everyone? Academia Global, it's the last time he typed his name. We have Isaac Waligo, Helen Atukwase. Some people had another T in there. Sometimes it is silent. Alan Baleke, Haifa Kariuki, Flavia Navendene, Israel, Megade, Ugola Ronald, Ronela Nambi, Ojede Benjamin, Matanda Press, and Chencha Samson, and then Twile Chris has left. I hope his network is coming back. I don't know whether people have resorted to just having the recordings later, but you can save so much, but I would advise that you're there live in the moment. You can ask questions and you can participate. So there are more solutions than problems in this world. Now, so you have a class of about how many? Now there are 195 plus 84, that's 170. 170 what? 76. Yes, so you have quite a big class, and the participation is a bit low, and given the feedback I'm seeing, people are not engaging as much. So again, make sure you check on somebody so that they can be here, because there's a temptation to miss class. Already the physical class had those a few issues, so you might imagine the online class is much easier, and it is entirely a different construct. So let's continue. You have Euler's formula, and then this Euler's formula is, you can express this exponential in terms of cos and cosine. So ei theta is cos theta plus. So that E is the same as ej theta. We're just going to increase the size of this. So ej theta is equal to sine, okay, first cos theta plus I sine, we need more space, plus I sine theta. So we had used J. So I and j is the same as the imaginary plane. So you have the real plane, and then you have the imaginary plane, which is j or I. So a number of books use I. And then similar to this is you have e theta without the j will be equal to, I don't know if you can guess, but you can multiply it through by j, and then you'd have e theta should be in terms of sines and cosines. You can nope, 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 nope. I think you should be having cosh and the hyperbolic sign. So so it should be cosh and then shine, but I don't know which one comes first. So it doesn't give you cos and sine. Eh? Let's just see here. So anyway, the thing is that you can express these cosines and sines in terms of the Euler identity. So cos theta is going to be given by there's a small error. So you can use E negative j theta, so that you have cos theta minus j sine theta, because cos negative theta is going to be equal to cos theta, and then sine negative theta is negative sine theta. So if you add these two up, cos theta is going to be ej theta plus E negative j theta. But remember, there are two of these, so this will be divided by 2. And then the same for the sine. It's just that in this case, you'll have to subtract the 2 of them. So sine theta, sine theta is going to be equal to, we don't have space. Let me just see if there are people waiting outside first. Because my sound is not on to admit everyone. Okay, so I think everyone who was outside is now in. Yes, we are saying that sine theta is gonna be equal to, so we'll just subtract these two, so it will be ej theta minus e negative j theta. So in this case, you didn't divide by just 2, you divide by 2j. So that is how you get this back. But so you remember that your wave function was given by, does anyone remember? Cos kx minus omega t, right? So sometimes you have an amplitude, eh? So that is your wave function. And then what else did we have? I think there are two waves in that bit, but just looking at the cosine bits, you just have kx minus omega t. So, but for the wave function, you have phi is equal to a cos kx minus omega t, then plus or minus b sine kx minus minus omega t. Now, who can express this as in terms of the real identity? This is going to be a exponent. You know that sine this is gonna be j into kx minus no, there's a meme of how normal people write x versus how we write x. So some people write x like this, sometimes you see it written like this. But that's not the discussion for now. So this is going to be your wave function. Now we assume Schrodinger assumed this wave function. The wave function in itself, we said, doesn't carry a lot of meaning, though we are going to see a lot of meaning in the subsequent lectures of the Schrodinger equation. So you had this. So this is how you end up with this, and then so that should be clear enough on how you get the exponentials. You did already that worst case at A level, but even at O level, if you did some more math, you should have been able to have that, or in your engineering math. It's just admit a few more people. The Mujungu praise. That's it. So given that background, we can have a new bit, psi, the wave function is equal to a exponent j into kx. Let me just use the other kx minus omega t. So now that we are there, we have already had the leading up to the Schrodinger equation, which I'll just get from here. And we say that we need to know a number of things that about the Schrodinger equation. One is that it has a de Broglie wave. So I feel weird calling it de Broglie, knowing what it is, de Broglie, but we have been using de Broglie emphasis. But it is de Broglie. So you have a de Broglie wave, and then that is one of the, this is from the wave particle duality. Wave particle duality. And then, so here the title should be leading to the lead up to the Schrodinger equation. to Schrödinger. I can just put umlauts here so that you know, to the Schrödinger equations. That is the title. Let's be a bit more patient in sort of underlining it. So we know that, and this of course determines the behavior of the electron. We'll have a short video at the closing to explain it in context. So electron, let me just write electron. So we are looking at this to determine the behavior of the electron. Now, one other thing we know is that, which is from the notes really, that the total energy is equal to the kinetic energy plus potential energy. There's a reason we had an X. We're going to see that plus potential energy. So that is the total energy. So sometimes, okay, it's not that, it's conservation of energy really. So let's just write that because we don't have a lot of space. So this is the law of conservation of energy. So now we have two things. We have this de Broglie, we have the conservation of energy. And so how do we proceed from here? Now, the next bit would be to substitute for these terms into this bit, what we know already. So those two conditions are for now enough to get us what we want. Now, some of the terms we want are up here, so we'll find a way to get them to where we want. K is equal to 2 pi over lambda, and then omega is twice 2 pi nu, or 2 pi f. For those who are, you don't have to be left behind. So nu is frequency. And so what we want to do is to get our energy. We know that from the Einstein, well, I don't know why you call it Einstein relation, but it's really Planck. We know that E is equal to H is equal to HF. And so from this F, we can see that F is omega over 2 pi. Let me just see if there are people outside here. Okay, some will come over. I think we have, okay. So I think people keep going on and off. So E is equal to HF, and so we can represent this HF by, okay, let's write the H because that also has a meaning. So let's get back the pencil. E is equal to HF. E is equal to HF. Planck's energy. Energy law. So Now F is omega over 2 pi. So if we substitute this, we'll have E is equal to H bar times omega, right? So we can write this in terms of, if this is equation 1, and then these are equations 2 to, let me see, 2, 3, 4. Those are equations 2 to 4. That's equation 5 to 6. So we can substitute for equation 6 into 1. So we have H bar omega is equal to, now the Ke is given by a half mv squared. Let's use one of the, Ke is equal to a half mv squared. And we know that mv is equal to p times m. So this becomes p squared over 2m. Because p is equal to, momentum is m times v. P is equal to m times v. So we can represent our Ke by p squared over 2m. And then we are left with potential energy now. And then potential energy is just BVX, because you don't know the potential. Actually, you're solving for the potential. So sometimes we eliminate the X to make the discussion a bit easier. So sometimes we just include it. So now we have this equation, H omega is equal to P squared over 2M. Now we can get we can get lambda. We can get lambda, and so lambda here. So from de Broglie's hypothesis, so this is the de Broglie wave. So from, so let's just box in this equation. From the de Broglie hypothesis, lambda is equal to H over P, right? So we can just substitute for P in this bit. So that would be, so that would have been equation 7. That would have been equation 8. So on Avera equation 9. So we can just substitute. So we'll have H omega, H bar omega. Let me see if there's anything in the chat. Nothing so far of significance. So H omega is equal to, so that will be inverted. P is H over lambda. So it will be H squared over lambda squared m twice plus v. Let me use that. Let me take advantage of the infinite scroll. Infinite scroll. Let's zoom back. So now we have these bits here, lambda, in terms of k. So we can express actually this in terms of lambda. It's gonna be a bit fast, but you guys should do some of the arithmetic. So we see 2 pi over lambda, that is h. So you can multiply this by 2 pi. So that means we'll have to divide through by 2 pi. So it will be h bar squared over 2m, and that is going to be k squared plus v. So that's equation 10 to 11. The last one is 11, this one is 10. So, okay, we go forward and so we have this equation, and then we have the wave function. So let's just contrast the wave function here. Psi is equal to a ej into kx minus omega t. So we can say that if we differentiate phi with respect to t, we can get what? Our omega, right? So we can just do that, d phi dt. D phi dt gives us omega. Okay, so let's go ahead and do that. D phi dt. Some people find it very hard to differentiate exponentials. So if you find it hard to differentiate exponentials, the sines and cosines, you can use the sines and cosines. Now, there will be this j term here. And since we're differentiating with respect to t, there will be another negative omega, right? Oh, God. So there will be another omega there. So these are the terms from the differentiation, j omega. Because remember, once you differentiate ex, it just becomes ex, like nothing has happened. If you differentiate d e ax, you get what? A e ax. So something was happening, but it's just that here you don't have a constant. So we get d phi dt, and it's that. So our omega is sorted. Now you see k is squared, so that means we're going to differentiate twice with respect to k. So d phi, sorry, with respect to x, d phi dx twice gives the k squared. So we do the first one. Should we use gray? Let me see the chart, what they are saying. The chart is quiet. Okay, that we can proceed without the chart. But in case there's anything, you can always post it in the chat. So divide x is gonna be, okay, it's going to be, after the US election, we can go back to it's gonna be, somebody is expecting a negative, but okay, a times j, well, we'll get the negative ironically, but jk, a is already there, the derivative is there, so we end up with our recursion, j into kx minus omega t. Okay, smaller bracket. Then the second derivative, which is d2 phi dt, sorry, dx squared. What does this give us? We'll have a squared. No, guys, where are you looking? One of these a's is not there. Let's just cover it. Bum, 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 bum. So we are going to get the second derivative. Second derivative, h2. No, we need the pencil. So second derivative gives us, now it's this jk again, so it will become, I'm just going to do here. So j times j gives negative j squared, and j squared is a negative, so it will be positive k squared a, wait, j squared will give a negative. Guys, the one's confusing me. J squared is -1, so that negative is actually j squared. So let me just make it a bit more prominent. Negative, then you have the j into kx minus omega t. So we can now replace this. Do we need to label the equations? We have enough numbers, so I'm not worried. Which one do we need to label? 12, 13, 14. So we can replace 14 and 12 back into 11, right? So we make omega here the subject of that equation. and then replace it in 211. So we don't have too many steps. So omega will be, so you have H bar. Omega will be 1 over J, or negative 1 over J, d phi dt. Now, this A into that is phi, right? Stretch, huh? So it will be 1 over J phi. Oh no, 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 no. Oh no. So we have only one. Let me just use a different color so that even if someone was sleeping, they'll be able to find it. So that over there is phi. This bit here. Okay, psi. I see tables are starting to move. Which is psi. Let me see if there's anyone here. There's no one here. Still on waiting. This is making omega the subject. Make our omega and k the subject. So you just do that step and then substitute it there. And then we have said that this is psi. Then 14 and 12 into 10. So you just make this a subject. So you have 1 over, then the j will go this side, and then this will also go this side, and it will be phi. And then, so we'll have the equal signs. Then what else did we have on this side? H squared, h bar squared over 2m. And we're going to make k the subject. So this is k. So this is going to be phi again. I mean psi. So this is k squared psi. So if we make it the subject, it will be 1 over k. Sorry, we're making k the subject. So 1 over psi times the second derivative. But then there was a negative on the k. So that goes there. And then we are done. So we just add the v. Now, v is a function of x, so it's not like a constant. But let's again ignore it for now. So, but just know it's a function of x. Now, here we have if you watch the distinct Schrodinger equation, so we can multiply through by j psi, Do we multiply through by j psi? No. We don't multiply through by j psi. We multiply through by psi. So we multiply through by psi, which is this. Or so you have negative h squared. So I'm going to multiply by psi. Of course, if we multiply through by psi on both sides, we'll end up, it doesn't change the equation. So I'm trying to avoid using red, but let me just use it. Sorry about that. So this becomes negative h bar or h over j d psi dt is equal to negative h bar squared over 2m d2 phi dx squared plus v psi. So that is our Schrodinger equation now. So we just have this term here to take care of. And this term is actually, it's the energy term. So because if we take away this, you remember that this d phi dt here is omega j psi. Yeah. So this term here is E psi, E times psi, because this was our E, which was h omega. So the only thing which changed was we multiplied through by psi. So this whole term is actually E psi. So E psi is equal to, I'll just make an exception and write an extra step, negative h squared over 2m tuli mwavu yeah, tuli mwavu. So okay, we need to touch up on the m. So that is E psi. Now, because of this negative, there's a negative which came in, and that negative was because we had this negative omega. So it becomes negative E ops. Oh, wait a minute. It's actually positive E psi because why is it positive E psi? Because omega is omega j psi J psi. So that is just omega J. Psi. The derivative. So if you multiply this bit here by omega J psi, it watch omega J psi to be negative. If you rationalize this, it becomes J. J times negative J becomes positive and becomes negative. Does it matter? So H. So if you multiply this J up, it becomes minus J, then J squared here becomes negative. It becomes a positive J. And then this is omega J psi, the derivative. So J times J is negative. H omega psi. Oh, this was negative J psi. So yeah, that becomes positive. So when you multiply this J here, to rationalize it from the denominator, it becomes positive. And then if you multiply back the negative J of psi, we end up with a positive. So yeah, so that's going to be positive. And so finally, we can write the Schrodinger equation as negative h bar squared over 2m plus v psi minus e. So, okay, let me first write it like this, is equal to 0. So there's a second derivative here. Second derivative, that d2 by dx squared. So basically what we now have is negative h bar squared over 2m d2 phi dx squared plus v minus e psi is equal to 0. Now, this is what we call the time independent misuse of years of drawing straight lines. So this is the time independent Schrodinger equation. So just a 1 minute recap. We should be powering the exponential rather than a. Did we have an 8 with certain power somewhere? Unless we missed the exponential, but it should be exponential something. Okay, we'll just correct that by adding the exponential. So, thank you for that observation, Farouk. And yeah, we're just missing the E in excitement. So I've just added it there so that it's like obvious. What else? Even this. I think it's when I shifted this. What about it? Yeah. Yeah, no. JK. It's almost inconsequential, but it's important. So we'll exaggerate the E there. I think that should be clear now. So that's a time-independent Schrodinger equation. And it's written slightly. Sometimes the E phi is on this side, and then okay, when stopped on 14, that would be 15. That would be 16, 17, 18, and then 19. So that's the time-independent Schrodinger equation. Now, the bit of time dependence is added by something interesting. But we can get, do we need the time dependence now? Okay, we can get the time dependence by a few manipulations, but well, we just multiply through by, okay, let me just share this screen. So let's wait for it to show up. Yep, I think it has shown up for most of the people there. This in the notes you're using sines and cosines, so you can go ahead and just follow through using sines and cosines other than you'll sorry about that. And so it yields the same thing, the same equation, time independence, and then the time dependence is okay, you will just correct a few things. You don't need to correct much, you know. There's no need to correct much. But you guys have learned about separation of variables. So you remember you had your wave function as phi is equal to this, right? Now, what you do is, can I just print screen this? Make my life easier. Print screen, let's move a bit more. No. You just pin the screen and then, okay, yeah. I can now print screen. I'll just cut out a few things. You also don't need this. The time dependence is added by, so you can just have a title here, time dependence. Name this thing here. Time dependent. Hey, it's looking weird. Don't worry, I'm going to share this screen with you. So since the content is not changing, I'll just share it because I'm monitoring this closely. So let's stop presenting and start presenting again. Back to our painting. Yeah, so we're now deriving the time independent equation. So you had this equation here, which we wrote as psi. Let's use another color. Psi is equal to a exponent j kx minus kx minus omega t so what do we have now? Yeah, so you still have the same thing. Now psi is a function of x and t, and we can solve these separately because the x variable and the t variable are what you call orthogonal. So in terms of these exponents, it's the same as a exponent jkx then times e negative j omega t. Yeah, where's the lie there? That's what we have. So once we're separating those powers, it's multiplying these two. So this function here is lowercase psi x, and then that is the theta t. So theta is also another function, like how you have psi. So it's like f of x. So theta is just denoting the function. So this is what you call sometimes linearly separable or something like that. So you can work out these two independently and then get, so if we differentiate with respect to x, theta t, remains constant, regardless of how many times we do that. And if we differentiate with respect to t, phi x becomes constant regardless of how many times we differentiate. So we can get those two derivatives for, remember in the Schrodinger equation, this is a second order derivative, and then energy was first order derivative. But we are going to see that. So if we do the second derivative with respect to time, do you even need it? I think we just need dphi dt. Dphi dt is simply psi x psi x d theta. Sorry about that. D theta dt. I think that's what we need only, because this would, you just multiply this by theta t, but then this doesn't multiply through by theta t. So of course, theta is the time independent variable. So in terms of when you're differentiating this with respect to t, you have a j, which is that. And then this side you don't have a j. So you have the normal derivative dphi dx and then theta t. And you have another, j phi d theta dt. So if you, once you divide this through, okay, sorry, you have this theta t from the derivative, and then this is just your function which you had as psi. So this theta t is from separating the other variables, so this remains constant. So now you end up with something like this. On the other side, of the energy side. Now, we can see this as okay, there's another equation for solving this. So, I mean, another condition for solving this, that if you have variables on this side and variables on this side, then the solution must be a constant. That is what we're saying. So we introduce a constant here, and then after introducing a constant, we can call it E or T or whatever. So if we use the constant E, then we can use the natural log. We can integrate this, and then so this will be d theta dt is equal to E times what? E theta t E over H, right? E over H, is it H bar? So the theta dt is equal to E H bar theta t, right? You had a J somewhere. So if you integrate both sides, let me just use, you end up with theta t as so the integral of this function here, you put back your theta t is simply this function here, ej omega t. omega t. Now that's good. That means it's going to be with respect to dt. Now integrating that is going to give you the time dependent Schrodinger equation. So of course you'll have something like I haven't missed out in the negatives, but okay, you'll complete this integral, but the answer should be the reverse of differentiation. So you multiply through by j omega. And after multiplying through by j omega, oh no, oh no, 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 no. Sorry, there's a small mistake, I think. So that should have been the theta t divided by theta t. So if you integrate this other side, you have, so this is the same as integrating the integral of 1 over x, which is the natural log of x, or in x. Why is this thing so aggressive? So this is the theta over, I mean, this is like 1 over theta t, or the theta over theta. It's gonna look a bit confusing, but the dt goes this side. And then you're integrating the theta, 1 over theta t with respect to theta. Yeah, so these two variables will be separate. Sorry about that. So this will be natural log of theta. So this doesn't work anymore. Just take it out. So that will be ln theta to ln theta t is equal to Et over h. So you remember 1 over j is going to be negative j. So that is it. So we can now get theta in terms of so theta t. So if we do exponent on this side and exponent on this side, you need to change color. if we do exponent on this side and exponent on this side, we have theta t is equal to, are we going back? Theta t is going to be equal to exponent j e t over h bar. I think this should be h bar. That looks a bit weird. So that, yeah, that's it. Yep, we have it there. And E is equal to H omega. Yeah, so we still get what we want. So you realize it's just multiplying through by that EJ omega t. This is the same as E J. Remember, E here is equal to H bar omega from up there. So if you multiply this will be J omega t. There was a negative here which we missed. So the time dependent equation multiplies this by E J omega t. And I think we had an epsilon somewhere. Did we have an epsilon somewhere? Sorry, E negative J omega t. Did we have negative epsilon somewhere? I don't think so. Yes, we had this as V epsilon. Where did this go? There's an epsilon missing here, the notes. Because once we removed it from this side, we had just phi x. Let's get this. So yeah, so we have just to cross check something here, something in terms of where this because we divided through by this product, so there's 1 over epsilon x, which is fine. This other side here had also epsilon x, and then that became 1 over epsilon that. So later on we'll multiply through by epsilon x, which is fine. So that should be that but let's just wait for this other side. Oh. That is too slow. We'll never get there. Let's look for university physics. Okay, the derivation is there in both books, university physics and also in understanding. Is the Schrodinger equation. It's the Schrodinger equation in this book. Remember it being there. It's chapter 14.
University physics doesn't have that of time dependent and any.
It used to have it. I'm just checking in this edition. It has the three-dimensional. It is quite the derivation. Let me first. They say it is difficult, but it is summarized to epic proportions. So the screen will be showing up soon. It has now. So this is the whole summary. Let's edit. Comment. Yeah. So this whole bit here is, they're referring to section 40.1, yes. But does it have? So section 40.1, the whole thing here is the derivation over there. So they just get this for a free particle. Maybe we just need to emphasize that we have been looking at a free electron. Okay. These are some of the solutions which we got on Monday. So background is there from the string, from the wave mechanics, and then it first goes with interpreting the wave function, which we have hinted a bit on, but then we have this wave function, define dxt. It doesn't explicitly state the time dependence. This is the time dependent wave function. You use it somewhere, anywhere. The time-dependent factor does not appear on the equation, yes, but what's the final one with time dependence? It should just be multiplying through by that et psi. So it should just be multiplying through by that e negative j omega t. Then times what? Times psi x. So here there's also an psi x. Okay, once it is no longer there, it becomes psi x. So let's just rewrite it, and then that will be the last thing we do today. Sorry, let's share this with you. Yeah, so it will become negative h squared, h bar squared, 3 over 2m d2 phi is over dx squared plus, so let's multiply through this psi x, vx psi x is equal to e psi x into e negative j omega t. So that should be the time-dependent Schrodinger equation. So the time-dependent bit, you have to go back and define the wave function in terms of this, and then solve that natural log, and then come to here. But most of the solutions that we use are time-dependent. So we just have to derive most of the solutions we use the time-dependent. So that's it for today, guys. I'll maybe take one question and then we're good to go.
Thank you.
So next time we'll look at the solutions, which is solutions. I hope we are still recording so I can stop.